This week's Friday seminar is presented by yourself. It's the title is CFAR then CFAR, a data-driven radar detector trained by LIDAR. I'll pass it over to you. Thank you very much.
Yeah, thank you. It's okay if I turn on my camera, so at least you can see my face while I'm talking. I think it's better. Yeah, cool. Yeah, so as Matt mentioned, I present this this paper on the IEEE Radar conference in Denver, I think a few weeks ago. And even though it's not explicitly mentioned in the title, all this talk is about automotive radar. So there will be some assumptions and some constraints that are imposed for these automotive radars, right? So I think first I will explain a little bit about automotive radar, very generic. Probably all of you know a lot about this topic, but just to give a little of context to this talk. So in automotive radar, it is very common to find high resolution in range and Doppler. We have a lot of available bandwidth, so we can have very, very good range resolution. But in the recent years, we are also starting to have very high resolution in azimuth and elevation. This is because we are starting to use MIMO technology, so we can have a larger visual aperture in automotive radar, right? And this high resolution azimuth and elevation is needed for the automotive scenes. And one of the characteristics of automotive scenes is that they are very heterogeneous, and we have very different kind of targets that we want to detect. We want to detect pedestrians, but we also want to detect cars, buildings, road infrastructure. And also, they change rapidly over time. You can imagine that you can drive at 100 kilometers per hour, and then things move very fast from one radar frame to the other. And also, one of the new trends is to incorporate more and more radars on the car. We have corner radars, side radars, and imaging radars, right? So the common processing chain of these automotive radars, well, this is the common processing chain for MIMO FMCW, right? Now they are some manufacturers, they are starting to do other kind of modulations, not FMCW, but still the standard is FMCW. So just as a quick recap of this signal processing, first you collect your ADC samples. Usually there are complex IQ baseband samples, and you organize them in fast time, slow time, and channels, right? So you do an spectral estimation to get range and Doppler, and then you have a range Doppler matrix per each of the virtual channels you have. And then you can do some angle estimation, right? You can do digital beamforming using Fourier transforms to make it fast. You can use compressive sensing. There are other subspace method, music, for example. So you do some kind of angle estimation. And then you have the 4D radar cube, which all the dimensions have already been performed estimation. You have range, Doppler, azimuth, and elevation. Then you have a detection stage. That usually in automotive radar is a CFAR, the Windows-based CFAR detection. And also maybe I can, use the laser point. Sometimes this angle estimation and this detection are swapped for performance, right? You do the detection on the range Doppler matrices, and then you perform the angle estimation only on those cells that have targets. However, then you are losing the coherent integration gain for the detection, right? Of the virtual channels. So if you can pay the price and you can do the detection after the angle estimation, this is, I think, the way to go. But of course, you have to do it efficient. And then after the detection, you have a point cloud. Many people use this representation level of the data because it's quite sparse, and then it's easy to handle. And then you can apply tracking algorithms or classification algorithms to know if it's a pedestrian or a dog, right? So this work is centered on the detection stage. And why it's centered on the detection stage is because I think the common CFAR detectors that are used, even though they are very nice for some applications, in this specific application, we are encountering some problems. So again, quick review of classical window-based CFAR detectors. So it has been proved that there are optimal detectors under some noise and clutter characteristics. And basically how they work is you have a window, a predefined window that you convolve over your data to estimate the noise or the clutter level. And then based on some statistical tests, you set a threshold, right? And the parameters that you have to estimate, they depend on the targets to be detected and also on the noise and clutter characteristics of the data you have. And I would like to mention also another kind of CFAR detectors that are subspace detectors for distributed targets that are used, for example, in maritime applications, which also they are CFAR, right? They maintain this constant false alarm rate, but also you have at least some kind of window. So you have to know a priori the size, the expected size of the targets you want to detect. So this is what I haven't find in the literature that most of the people do on automotive radar data, but there is a few problems. So first, we have non-homogeneous clutter, but I think we have there is a more philosophical question on what is clutter in this problem, because basically we want to detect everything. So we want to detect the buildings, the pedestrians, we want to detect the road infrastructure, we want to detect the bridge, if there's a bridge, the tunnel entrance, the road. So the definition of clutter is not even clear in this problem. Then the objects we want to detect, they have very different sizes. As I said, you want to detect a tree, but also a dog. But there is a more subtle problem with the size of the targets. That is how extend a target is in angle. It depends on the range. So, for example, a car in a very close range, it might occupy many angle cells, but when the car is at 200 meters, maybe you will perceive it as a point target. So we know also that at millimeters waves, the targets are extended in Doppler. So you have already mentioned that different objects will extend differently. For example, a pedestrian moving the arms will have a different Doppler extension than a pedestrian standing still. And then if you think about the subspace detectors, the problem is that they are basically it's almost a brute force approach where you are trying to coherently integrate the power in the adjacent cells by some steering vectors. So the question here is how we can tune the parameters of the CFAR detectors, of the window sizes, for example, of the parameter detectors, given all these problems, right? So this is the main challenge. And the good thing is that, okay, CFARs use, or Windows-based CFARs, they use a single window with a single function. If you imagine a CA CFAR, for example, a cell averaging CFAR, you have a Windows size where you do an average, and then with that you estimate the average noise level. So what if using only one single function with, a single window with a single function, why we don't select many different window sizes? We just stack them all together, and we let a machine learning algorithm find the right parameters for this. And if you think about it, this is a convolutional neural network. At the end, a convolutional neural network, what it does is it takes a kernel or a window and slide it over your data and estimate the parameters of that window based on the data you have and the loss function you have. So we can use data to find the optimal parameters of these windows, but then we have a problem. It is that when you have data and you want to train a machine learning algorithm on data, you need ground truth. And there are two problems here. First, that radar data is not human interpretable. If I show you a 4D radar cube, you are not going to be able to distinguish what's inside. So we cannot manually label things. So the approach that we have followed here is why, if we use the best sensor available, to label our radar data. And the best sensor available right now, they are LIDAR systems. So what we have done is we have taken a car from the intelligent vehicles department that they have different sensors mounted on, and we have also mounted an imaging radar. It's a commercial imaging radar, a MIMO FMCW from Texas Instruments. And we have collected a lot of data. So we have started driving around, and we have drive on many different parts of Delft, which is the city I live on. So we have scenes in the city center that are very crowded with a lot of bicycles moving around, high buildings. Well, high, yeah, not very high. It's the Netherlands. Buildings, let's say. Then we have also data collected in the countryside, much more open space. We have also drive around campus, that is a different environment. And we have synchronized all the sensors, time synchronized, but also spatially calibrate them. And we have a huge, interesting data set that is online already. If you enter in the reference that is in the bottom, that's a GitHub that it has code to use the data, to process it, and also a link to the data itself. It's quite heavy. It's, I think, almost 2 terabytes. So be aware of it. But you have the data, so you can use it. And for us, what we have done with this data is, going back to the detectors, is use LIDAR as the ground truth to train our detector. So I will explain. This is an overview of the full processing chain. Let's start with the radar, which is the thing we are more familiar with. It's a quite a standard processing chain. We do windowing and to the FFT. The only problem here is that we are using TDMA, so time division multiple access. So there is some algorithms you have to do to extend the unambiguous Doppler and to do some Doppler correction due to the different transmission times. This code is available, by the way. So then, because our array is sparse, we do some zero filling, just easy, and then we crop our in a field of view to try to avoid granting lobes. So it's quite a standard processing chain, and then we train the network. But to train the network, we need the ground truth. So what we have done is a processing chain of the LiDAR also, that I think is better if we see it visually in the next slide. So LiDAR is a 360-degree sensor. So if you see A, this is basically what the LiDAR gives to you. This is a point cloud. This is if you connect your computer to the LiDAR, this is what you get. But we know that the radar has a different field of view. It's not a 360-degree sensor. So the first thing we do is we crop the LiDAR into the same field of view of the radar. And then what we do also is we remove all the ground points because of the shallow angle that we have with the radar. Most of the road doesn't have reflections. So we employ an algorithm called Patchwork ++ to do this, and the result, you can see it on the right image. And as you can see, the image is quite clean. You can even by eye see here the cars or the trees, or so you could use this data. But now, to use this as a ground truth, we have to voxelize it in the same way as the radar. So we know that the radar doesn't have a fixed grid. For example, because of the array topology, we have much better resolution at bore side than if we look at far end. So we have to take this into account in our ground truth. So basically what we do is we take this LiDAR point cloud and we voxelize it in the same way the radar sends the scene. So we can use it as a ground truth. So once we have our ground truth ready, we can train our neural network. So this is the neural network I am using. And each of the steps have a meaning. I will explain slowly. So the input of our network is 2 3D cubes. This is basically to save space because the dataset is quite huge. and the power we encode it in a float, and the elevation radar, the elevation, sorry, is an index. You can store it in an int, basically the bin index. So this is just for efficiency. Then the second part is we call it Doppler encoder, because LIDAR does not provide Doppler, so it doesn't measure speed, but we have that information. So the easiest way will be just to drop the Doppler information. But we know that there is a relationship between Doppler and angle of arrival because of the projection in the radial speed. This is used, for example, for Doppler beam sharpening or for SAR, for example. So we have useful information in the Doppler. We don't want to throw it away. So we employ this structure of convolutional layers to extract the maximum Doppler information. Then we use a segmentation network called feature pyramid network that, if you remember, this is what we talk about, is windows of different sizes to account for the different sizes of the target, of the different targets. So we have used this pyramid structure with different sizes of the windows. And then the output is a 3D occupancy grid in azimuth elevation range that contains ones where there are targets and 0 otherwise. This could be understood as a detection mask. But to train this network, you have to overcome some challenges. So first of all, the data is highly imbalanced. So if you look around in wherever you're in a room, and most of the space is empty. So most of the voxels don't have target. So you have to carefully treat this. And to treat this, we use something called focal loss. And this is some sort of generalized weighted cross entropy that you have a parameter to control the sparsity level that you want, or that is in the scene. And this parameter can be related to the probability of false alarm. So I don't have a mathematical expression to relate these two parameters, but empirically, I have seen that this controls the probability of false alarms, basically. But what is interesting of this focal loss is that it has an extra parameter to weight the hard cases. And I will explain what I mean with hard cases. So if you have a very reflective target with high SNR, probably almost every detector will detect it. So there are easy examples. But on the other hand, if you have a small target with low RCS quite far, and the SNR of that target is low, then it's harder to detect. So this loss can put the focus, and that's why I call focal loss, on the hard cases. And this is very, very interesting for radar data, especially because we have a very large kind of target that we need to detect. So what we have done now is take 5 of the 7 scenes. So each scene is an independent recording in a different place with different characteristics. We have taken 5 of that scenes, and we have used it for training the network. And the rest 2, we have used them for testing. And all the results you are going to see in the next slides are evaluated on these 2 scenes. So it's unseen data for the network. So first of all, we will see some qualitative results before going into some metrics, just to show some examples. Yeah, so here you see 6 plots. The one in the left is LIDAR, the one on the middle is the proposed method, and the one on the right is the best CFAR I could get. I will explain which CFAR it is. I will use the laser pointer. Yeah, so on the LIDAR, you can clearly see the projection over the camera that you can detect very well the pedestrians and the cars. Here, the cyclists, sorry, no, they're not pedestrians, they're cyclists. In the Netherlands, there's not many people walking. Almost all the people go with bike. So in a blue shape, it's the cyclists, and in the red shape is the cars. Here in the middle, you can see the output of our detector. You can see that every target is clearly detected. And on the right, you can see output of the best CFAR I could get. So if you look at the top view, you can still see the detections. So the CFAR is doing the job, is detecting all the objects. But when you see at the projection of the image, you can see that the result is it has much more noise and much more false alarms, right? So this is just to give an example. So this is another example. Here, what I wanted to highlight is that the shape of the target is maintained with the proposed method. For example, if you have a look at the cyclist or at the cars, you can see that more or less the shape of the detected target is maintained. Here in the LiDAR is quite good, is rectangular shape, but here still you could use that shape information. While on the CFAR, you lose that. And you lose that because at the end, these Windows-based CFARs are enforcing peak-like detections. And then you lose that capability of the shape. Again, this is only some examples of the CFAR, but it's just a visual example of how it looks. But of course, we need metrics, right? So I have used 3 metrics to evaluate the quality of the detection. The first 2 are common in detection problems, is the probability of detection and probability of false alarms. But for this specific case, because we are using LiDAR as ground truth, I think they are not good metrics, and I will explain why. So I have used another metric called chamfer distance that it evaluates the similarity between 2 point clouds. So basically, for each point in each point cloud, it founds the nearest neighbor and compute the distance. And then all these distances are added. Here you can see the formula of the chamfer distance. But I think it's better that we see it visually here. So if you have, by the way, in this example, the 2 point clouds, they look the same and they have the same number of points. But chamfer distance is general. You can have different number of points in each point cloud and with different shapes. But you can see visually that when the 2 point clouds perfectly overlap, your chamfer distance is 0. And when you start moving around the other point cloud, the chamfer distance raises, right? So I will elaborate on why I think this metric is better, but let's have a look at the results. So I have tried many CFAR detectors. Most of the time of doing this work, it was trying different CFAR detectors with different window sizes, different parameters. And these are the best performing ones. So on the top row, you can see the proposed method. You achieve a 65% of probability of detection versus LiDAR, while all the CFARs, they have very low probability of detection. And I can explain why. But for me, the most important thing is the chamfer distance. So we can see that we are achieving about 3 times better chamfer distance with the proposed method. By the way, here the RA and D, they stand for range, azimuth, and Doppler. For example, the first CFAR is a 2D OS order statistics CFAR in range and angle. And then I do a 1D OS CFAR in Doppler. I don't do a full 3D OS CFAR because the computational complexity explodes and it's basically impossible to compute it in a reasonable time. But let me explain in detail why these numbers and if they make sense first. So let's have a look at a mock example. Let's have a look at the ground truth. We have 2 detections illustrated here as the green ground truth. So let's have a look first at A. What happens if we have 2 ghost targets? So we have the worst detector ever. We completely miss our targets, but we have 2 ghost targets. So in this case, the probability of detection is 0. We have 8% probability of false alarm, and our chamfer resistance is 4. Okay, these numbers, as it is, they don't tell us too much, but let's compare to a different example where we have 2 targets detected. They are only 1 cell shifted, and this can be, for example, a miscalibration in the alignment of the sensors, right? Remember that we have very good resolution, so these cells are as small as 20 centimeters. So If you have a small miscalibrations in the pointing angle, for example, this may happen. So in this case, the probability of detection is still 0. The probability of false alarm is still 8%, but our chamfer distance is 2. And why is this? Because, to be honest, this case B is much better. We still detect the 2 targets, they're just slightly moved. But that is not reflected in the probability of false alarm or in the probability of detection. And this is why the probability of detection of CFAR is so low. And I think that's one of the explanations, because the network can learn these offsets, but the CFAR cannot. So if you have calibration errors, the probability of detection will, calibration errors between the LIDAR and the radar, the probability of detection will drop completely, even though it's not that bad. And in the last example, what we have is what I think is happening, because the LiDAR resolution is much, much better than the radar resolution. So most of the targets are overestimated in size. So then you have your 2 true detections in blue here, but also you have your shape that is bigger because your resolution is worst. And then you will have false alarms. So in this case, the probability of false alarm is the same, it's 8%, but you can see that the chamfer distance is smaller. So you are reflecting better the performance of the system by looking at the chamfer distance instead of the probability of detection and probability of false alarms. So that's why I'm saying that this chamfer distance, it really reflects better the performance. And what it means is that our method is performing around 3 times better than the CFAR, or at least the best CFAR I could make. So before finishing, I would like to show you a video of one example of the dataset. On the top, we'll see the camera. On the bottom left, we see the output of the proposed method. On the right, we see the LiDAR, which is always much clearer. And I didn't plot here the CFAR because it's very hard to understand, especially when everything is moving. So no worries, because the video will slow down. But I have tried to choose a very challenging situation for the radar, which is when we go under the bridge, because the bridge is closed on the side, so there's a lot of multipath, right? So it's one of the biggest problems in automotive radar. So when we reach that point, you will see that the video slows down, and on the red arrow, we can see the detection of the entrance of the bridge, and we can see that still inside, we can detect I will pause it. We can detect the bus, but also the cyclist that is next to it. That in the camera is even hard to see because it is in the dark region of the image because of the shadow of the bridge. But we can still detect it. And of course, it's not as good as LiDAR, but this is impossible to achieve. So this is just to highlight a hard example that is in the dataset. And remember that this data, it has not been used to train. This is only to test the performance of the network. In the dataset, you can find all these point clouds and all these videos that you can even play with them yourself. So this was just to show an example that it runs on real time. So to finish this talk, I just want to summarize a little what I have done. So the main message is that we have trained a deep learning detector using LiDAR data. But after it's trained, you can remove the LiDAR and just use the radar. And this algorithm, this neural network, it achieves 3 times better chamfer distance with respect to when you compare with LiDAR, right, than the standard CFARs. And the CFARs I have compared, believe me, that is everything I could try. I have tried different size windows, different hyperparameters, different type of CFARs. But the good thing is that data is available and the code is available, so you could try to implement your own detectors and benchmark it against this neural network. And I think the most important point is that the data is available. So if you want to download it and play with it, just go ahead in that GitHub and request the access. And yeah, and have a look at it. So thank you very much. That was the end of the talk. I hope you like it, and if you have any questions, just tell me.
Okay, thank you so much, Ignacio, for a really interesting talk. You've got some really good results in there and really nice video at the end demonstration. I think everyone's attending remotely today, so if there's any questions, if anyone would like to raise their hand in the chat, and then we can go around